And we'll go ahead and get started with Tim's presentation on UEFI and the security development lifecycle.
All right, thank you, Brian. I'm sure that you're going to, by the time we get done with this, you'll probably be sick of security topics because no one gets paid any more money when you're secure. It just costs money to do it, right? Okay. My name is Tim Lewis. I'm the CTO with Insyde Software, and So just we're going to talk about the threat is real within firmware, within the UEFI BIOS space. A little bit about the security development lifecycle, which is how it works. What is it? Is firmware really worth attacking, and how your firmware actually gets hacked, and what you can do about it, and then a few resources at the end. Let's talk about the threat, just to convince people that the threat is real. If you're not already convinced, if security isn't already on your number one things, when you Google BIOS, UEFI BIOS right now, if security isn't already showing up in your top 10 items on your Google results, then you must be Googling something else not related to BIOS and probably not worth mentioning in this venue. But firmware holds a valuable place within the security, within platform security. And not just because of computer systems are only as secure as their firmware, but really what happens is the value of the data which is stored on these platforms. The value of the data on your platforms is much higher than the cost of your firmware to buy. Just think about it for a second. How much are your hospital records worth? How much are your selfies worth? Some of you more than others, maybe. How much are Bill Gates' selfies worth? Probably a little bit more even then, right? And if you consider the cost of firmware development for a particular platform, maybe it's 20K, 50K, 100K, whatever it is, and you compare it to the cost of the data like hospital records, or the value of the things like hospital records or Bill Gates selfies out there, you can see there's a big disparity between the value of the data on the platform and the cost of actually getting a hold of the source code for a very specific platform that you want to attack. Social security numbers, medical history, date of birth, credit card numbers. The difference between the value of the data and the cost of the BIOS shows why hackers are interested. Now, and if you also haven't noticed, firmware is under an increasing number of attacks. Now I have to say that the reason this is true is because the Linux ecosystem and Microsoft have done a better job at securing their OSs. There are still zero-day attacks out there, right? But the problem is it's becoming harder and harder to find those. They're becoming more and more difficult to do. And so hackers turn their attention to easier targets. And guess what? They found an easier target in us, in the people in this room. The unique security position of firmware combined of the value of the data on the platform means it is no longer just hackers but professionals who are interested in attacking. Conferences like Black Hat and DEF CON increasingly contain sessions that deal with firmware security. Trust me, every one of them gets emailed to me like 10 times after after Black Hat conference, trying to find out if our name was mentioned and are we vulnerable. The headlines are embarrassing, but professionals, frankly, are not after headlines. They are after valuable, embarrassing, incriminating data. I would also say that security issues present a unique challenge for BIOS vendors because attackers usually don't focus on a platform until 2 or 3 years after it's shipped. So just to give you an idea, as a BIOS vendor, we often have forgotten about platforms. We work on them, and then they go through the manufacturing process, and then they get shipped, and then slowly the number of units out in the real world starts to increase until it reaches a critical point, where hackers say there's enough of these systems that are out there that it's worth even writing a hack for it. And by that time, it's 3 or 4 years after the platform, we've stopped working on the system. So for BIOS vendors and firmware people, in particular, this is a unique challenge because a lot of times we've forgotten about this platform. It shipped so long ago. We have shifted which version of which EDK2 we're working with, which of our own kernels we've shifted 2 or 3 chipsets later. We ship hundreds of platforms a year, as do all the other IBVs, the IBVs in this room. So it requires a lot of new work on an old platform where tools, kernels, EDK2 versions, chipsets have already gone back 2 or 3 generations. As Microsoft said famously in their presentation on this, we, that is the people in this room, must be 100% correct, 100% of the time, on a schedule, with limited resources, only knowing what we know today. Oh, and the product has to be reliable, supportable, compatible, manageable, affordable, accessible, usable, global, doable, and deployable. They, that is the people attacking firmware, can spend as long as they like to find one bug with the benefit of future research. So we're never going to get it 100% correct, but we have to try and do a better job at this. One of the ways that we are looking to do it within UEFI at Insyde is the security development lifecycle. This is a process for developing demonstrably more secure software pioneered by Microsoft. And for those of you at Microsoft, I apologize if this seems like a rehash of some of the things that you probably got as within your first months of becoming an employee there. But I do want to talk about some aspects which are unique to UEFI and firmware. And I use a few different terms here. So we at Insyde are adapting this for our BIOS and BMC product lines. Why? Because it improves our ability to support, design, develop, test, and release secure software. First, we're using training. This is actually, pieces of this are parts of our training as well, to educate all of our engineers. We are also creating security experts to help other teams with security issues. Second, threat modeling. It's funny. There are threat modeling experts in this room, but no one wants to share their threat models. It's like, anyway. Third, we improving our coding standards and tools to minimize the chance of attacks. How do we implement our code? What coding standards? Restricted functions, best compiler switches. Fourth, supporting fuzzing for BIOS interfaces. And fifth, security review, and also making sure that we can actually recreate. ThinkPwn for us was a defining moment if you go back a few years. Why? And because it required that we had to go back and update many platforms, some of which were very old for our customers. And that means that we had to go make sure we had the right compilers, because most of us have already tossed Visual Studio 2003, which was a long time ago. So even some tools were not even about. So how do we respond? How do we deploy fixes? How do we inform customers? And how do we update tests? All of these are a part of the security development lifecycle. Now, if you're thinking that this is a lot of effort, you're right. I mean, just EDK2 alone, UEFI BIOS is a big product. It's not an OS, but it is a big product with millions of lines of source code, covering quite a range of technologies, industry standards, and much of the code that ends up on your platform, if you're a platform developer, much of the code that ends up there actually doesn't come from you originally, right? Some of it's coming from open source, some of it's coming from your silicon vendor. So, it doesn't come from, not necessarily, it's not just the IBV who's responsible for everything. Actually, we get blamed for everything. So it doesn't make any difference where it originally came from, but as a BIOS vendor, we get blamed for everything. So it's a lot to do. And one of the ways that we, what do you do next? The sort of what do you do next sort of step is evaluating where you are, where are we as an industry. So let's see how we measure where we are. In security development lifecycle, we talk about this in terms of maturity. So there are 4 different levels that are defined in SDL: the basic level, standardized, advanced, and dynamic. So basic means we haven't done anything, or we're thinking about doing something, or maybe we've done something, but it's not been in a very standardized or consistent way. For example, one group in your company, one group is paying attention to firmware security, one team is for a particular product, maybe another team isn't really paying attention to it all. Maybe you have figured out how you notify your customers about security incidents, but the other parts of SDL, there's nothing happened here. At the standardized level, the second level, you do have some company-wide security experts. They're recognized as such. You're supposed to go talk to them. You have a general evaluation of your product in terms of high-risk areas, and you've selected a pilot project that you're going to focus on. Because remember, you've got 2 million lines of code. You can't go through and do a detailed threat model mitigation analysis for every single part of your product at one time, because it's just too much. So you pick a pilot, you pick a high-risk one and say, we're going to start learning this process on one area. And that's, you see how it works, see how it might need a further adjustment in your company. And when you've done that, you've reached the standardized level. There, in the Microsoft material, there are about 15 requirements for actually reaching the standardized level. The third level is called advanced. At this level, you actually have a security team who've done this, and they've gone through this process, and now you're bringing all of your development into having going through this process as part of it. Not just pilot projects, but in general, your projects are all being evaluated in terms of risk and going forward. And the dynamic level means there's quite a widespread security within your company, both at a centralized team and also within specific product teams. So each of these capability areas has key requirements. Like I said, going from basic to standardized, there are about 15 requirements. Where is your company? If you think about it in your mind, if you were to review where your company is and say, where am I in terms of doing this kind of analysis and these kind of things, you should place yourself on this, and that helps you get an idea of what are the next steps. And some of the resources that I'm going to mention at the end help you to do a self-assessment of your team or your company, and also to give you guidelines as to where you might consider going next. That'll be on the final one. Now, one of the key items within the security development lifecycle is Insyde. So we're looking at threats here, and these are categorize the risk types according to this acronym. There we go. Acronym. There we go. I'm an anachronism. This is an acronym. Okay. The risks are what could hackers do if their hack is a success. All right. Now, some people have variations of this. I've seen Stride, various things, but I'll use the basic ones from Microsoft's material. The first four are not as common for bias, but we'll cover them so you know what they are, and then we'll go through the ones that are the most at risk for bias. Spoofing. Spoofing is impersonating someone or something else. For example, if someone sends you an email and says they are the prince from Nigeria, and you believe them and send money to them, we can say they have spoofed you, right? They pretended to be someone else. They pretended to be someone who should have had higher privilege or access. If you are at Anonymous and you are able to log in as Bill Gates, you have a lot of access at Microsoft. That's spoofing. Second, tampering. Tampering is modifying code or data so that the behavior of the bias is changed. For example, if you were able to tamper with the secure boot variable DB, you can change the bias's behavior to what? To allow another OS that's not actually authorized to execute. If you tamper with the Dixie code, you can modify part of the SMM code. That's tampering. Repudiation. Repudiation is pretending that something happened when in fact it did not. For example, if a lot of us would like it that if we went to our ATM machine and we withdrew $100,000 from our bank account, and then we said, no, I didn't actually withdraw any money whatsoever, that would be repudiation. That is saying I didn't actually do something when in fact I did do it. Fourth, information disclosure. Information disclosure is getting access to information that should be protected. For example, if you can read the BIOS password, or you could read the root password from Linux, or you could read the ongoing HTTPS session key that's being used in the middle of a transaction. If you could do those things, that's information disclosure. So let's look at some common types for bias. Oop, except that I don't want to do that. Denial of service. This is very common. This is the most common. If you see all those reports of, gee, I filled up my entire UEFI variable store so full that and on the next boot, it wouldn't boot anymore, right? There's a denial of service. That is denying or degrading the ability to use the system. The system won't boot, or the system can't enter setup, or the system stops supporting suspend or standby. Now, another version of this is called the permanent denial of service, or PDoS. That's called bricking. It's when you brick the system, when the system no longer responds at all. You know, we had the case last year when Ubuntu OS and the Intel SPI driver and the BIOS had a little bit of a communication issue with regard to SPI opcodes, and you had a denial of service. Elevation of privilege. Another class of attacks that's very common these days is an attempt to gain elevation of service by using the BIOS. One of these is being able to insert code or data earlier in the boot process and have things happen so that you can gain control over hardware registers or hardware resources or information resources that you normally would not have access to. Another way to do this is being able to convince the SMM or management mode or trust zone code, if you're an ARM side person, to do something that it normally wouldn't do, taking advantage of its very privileged location and position within the system to get a hold of people's information, take over the system, do things you want to do. So elevation of privilege is another large thing. So these are all just ways to categorize the different types of risk. There's another way called DREAD that talks about the way you evaluate the damage, which we're not going to go into today. Now let's look in UEFI. Just in general within UEFI, there are things called, you have trust boundaries. That is, data which crosses a trust boundary is something that's always very suspicious. You have to watch out for it. And within UEFI, these trust boundaries, as we go through the boot process, the trust boundaries get bigger and bigger and bigger. That is, they incorporate, they're executing in more environments. They're coming from different sources, and they interact with more devices. So as you execute in more environments, and as you get code from more different sources, and as you interact with more devices, that your attack surface is getting bigger, your trust boundary is getting, there's a lot more things going into your trust boundary. So in UEFI, this starts very early within SEC and PEI. So within SEC and PEI, the code is running from Flash, so it's relatively hard to modify it, right? Early on in SEC, it's not like there's no DMA attacks, usually. No DMA attacks while you're running out of Flash. Usually no one else has had a chance to execute. I'm skipping crisis recovery. Yes, for those of you who are grognards in the UEFI realm, I'm skipping S3 and I'm skipping crisis recovery boot paths. Okay, we'll come back to those. But you're running from Flash. The code usually only comes from the IBV or the ODM or the silicon vendor in EDK2. That is, the number of people that the code comes from is pretty well controlled within these spaces. There's no third parties other than the OEM has controlled exactly what they want to be in their board usually. And during these, there are very few phases. There are very few devices that you're interacting with, right? What do you got? The SPD DIMM, you've got the soft straps, you've got maybe a couple jumpers on your motherboard, but there's not a lot of hardware resources that you're interacting with, and data comes from UEFI variables as well. So it's a relatively small and contained. Now, as we go a little bit further into Dixie, we have the code is now running from DRAM. There's now also code in SMRAM, so we have now introduced another environment. There are interrupt sources. Code still comes mostly from the same set of people that it came from in SEC and PEI. We haven't added to the number of code providers yet at this point. There are a few more devices like SuperIO and PCI device config space. And at the end of this phase, we lock down the SPI part and we should be locking down MMRAM or SMRAM. Now, when we get to the boot phase, BDS phase, now things start getting interesting in terms of code providers, right? We start adding other people who might have provided code, whether it comes from an option ROM, whether you've got a driver coming from the driver ### bootlist or sysprep. Then there are more devices. You've got tons more devices to interact with because they're all the different boot devices. Finally, we're going to get to runtime. The OS bootloader starts going here, and it starts even adding more devices, more third-party code. So there's a lot more people. And finally, we're under the OS, and you've got applications and even more devices. So just to point out is, the later you get in this, the more at risk you are. If earlier you get hacked, the more danger it is because you're now affecting more and more code coming later. Where would I look for weaknesses? I'm going to make some assumptions here. If assuming that flash is protected correctly and I'm not worried about DEDI-prog attacks, okay? And assuming that this is not a physical DRAM attack and not a DMA attack, and assuming that the attacker has source code to my platform, where would I look? Well, first of all, software SMIs, or software MMIs, if you're in the new terminology. It can be successfully attacked, and the hacker can get control of the entire system and have access to all of system memory, right? If you have access to it. So if I was looking at my code and saying where are vulnerabilities, a lot of them are software SMI attacks where I'm looking for buffer overflows, integer arithmetic attacks, these kind of things. If I can convince the SMI code to do something that it shouldn't do, it opens up a world of hurt. UEFI runtime services. Why? Because these services get called by the OS applications. That is, it's a lot easier for an attacker to deploy an attack and attacks UEFI runtime services because you can call them easily from an OS present, even a bootloader app. The S3 resume path, I skipped that on my previous diagram, but of course things like S3 resume path comes back while the flash part is unlocked again after having run OS code. So if there are pieces of data or the artifacts that the code in S3 uses, then they have access to flash before it's protected, SMRAM possibly before it's protected. So protecting the S3 resume path. UEFI variable data. Secure boot is only as secure as the variables that it depends on. So if I can go in and change secure boot from on to off, right? That would be a bad thing in terms of secure boot being secure. There are a lot of other variables that the UEFI variables that the BIOS deals with to properly configure the platform. If they can be modified, then your system is hosed. So protecting UEFI variable data and making sure that even bad data is handled correctly. Hardware device data. A USB device descriptor proved to be one of our problems. There was a bad USB device descriptor passed in garbage into the USB device stack. Guess what? The USB code did some rather interesting things after that point, like writing over large segments of memory that we weren't anticipating that it was writing over. Okay, so that points out that a lot of times what your BIOS is doing, even during the pre-OS phase, when your BIOS is interacting with hardware devices, especially config data that's coming back from devices, if that data has been deliberately tampered with, it is easy for your code to go off the rails if you are not careful with this kind of input. SPD data. There's classic attacks against SPD data if it's formatted incorrectly. UEFI capsule data. UEFI capsules are a very complicated data structure, and again, if they can be hacked, they are dealt with during a piece of the BIOS where, during a time in the BIOS when some hardware protections have not yet been enabled. And finally, of course, network packets. At HTTPS boot, you are entering into a world of new attacks which are well understood by the rest of the industry, but not so much by the BIOS industry. Okay, what can you do about it? Train your engineers on basic security concepts. It's got to become part of the basic education for any firmware engineer to know the basics. Do they know what buffer overflow attacks look like? That's why we had a presentation last time that I gave a presentation on different types of buffer attacks against software SMI during the last Plugfest. If you want, you can go look that up. But there are integer arithmetic attacks, those sort of things. Train your engineers on these basic concepts. Check the process of your code suppliers. If you haven't already, it's not a bad idea to ask the people who provide the code that you deal with what they've done in terms of evaluating their code's security. What process do they have in place for security? Ensure that you have all the tools that you need to reproduce your build. If you haven't done it yet, start with the riskiest parts of your code first and work backwards from there. The good thing about EDK2, this is a good thing, is that there are lots of eyeballs looking at EDK2, right? There are lots of companies who are paying attention to security issues for EDK2. But there's a lot of code that you've written that probably doesn't have quite as many eyeballs. So you might consider starting with the code that your company in particular has written that's not in EDK2 and work backwards from there. Use tests that focus on security, not just functionality. This is one of our weak points, I'll confess, is that we often focus in making sure that our code works in the designed use cases. But we don't always test for the cases, what happens if someone passes us a lot of bad data, malformed data. So test for focus on security and improve your tools. Now this is tricky for BIOS vendors because a lot of the traditional security texts say, oh, turn on all your compiler switches, like runtime code checking for buffer overflows and runtime code checking for integer loss of precision. But those always end up being asserts. Well, what is an assert to a BIOS engineer? It's a hang. An assert is another word for hang. So then you have to weigh, is it worse to get hacked, or is it worse to hang? Again, a lot of the, like for example, Harry, I'm going to look at you because I know you've got the stack guard stuff. A lot of the stuff in EDK2, which is great for detecting null pointer accesses and stack overflows and stack underflows and heap guard. Those are great things. But if the result is that in my running system it hangs, right? It's not a good thing for my end user if it hangs. It's not a good thing if they lose their social security number either. Okay, it's not a good thing if it hangs. So there's a little bit of a balancing act in BIOS. I can't just stop like I'm under OS, I can stop the process that's running if it has a security problem. But I can't very well stop the BIOS from running when it has a security problem, or I can, that's a hang. Okay, resources. The resources I have on the screen just give you an overview. Where to get started with the SDL, there's some basic training material there. There is a self-assessment guide for SDL saying where are you in this overall process and what things should you consider as next steps at each point in this. Threat model analysis we didn't go into, but basically it's how do you evaluate your design from a security standpoint. Things like trust boundaries, external entries, data flow, processes, those sort of things. There's some great training. There's even a threat modeling tool from Microsoft that's like Visio, except you draw your diagram. You put your little blocks in there and it generates a report for you that can help you to evaluate your design using their tool. And then basic security training, like the kind that I encourage you to use for every one of your engineers. Microsoft has a good version. It is OS focused. I will say, that is, it's focused a lot on on recommendations and security risks that are really OS specific, but it is good general material, and a lot of the great topics like buffer overflows and integer arithmetic stuff, it's excellent in terms of examples. And that's it. Questions? Yes?
Hang on.
Am I going to? Are you a customer?
The question was sharing threat models.
The question was, am I going to share my threat models after banging on other people for not sharing theirs? Yeah, if you're a customer, we'll talk to you about our threat models. Yes.
We've only got a couple of minutes
Sure.
of time, so it's probably take one question if somebody has one.
Okay.
Okay, well, Tim, thank you very much.
Yeah, I'll be here between 3 and 4 o'clock during speaker hours. If you want to talk to, in more detail about any of these topics in security development lifecycle, come during that time and I'll be happy to talk to you.
Excellent. Thank you, Tim. All right.